Okay, lecture 6. We are starting chapter 2. It's going to get more interesting now. Okay. And this chapter is called Descriptive Statistics. Remember, there's two kinds of statistics because you can use statistics to do two things. You can use them to describe a certain situation, and that's called descriptive statistics. Okay? Or you can use statistics to try to predict or infer something that is happening or is going to happen. So right now in chapter 2, we're going to talk about descriptive statistics, which is using data to describe certain situations. And what we're going to do today is cover a lot of different ways to graph data. Okay? Some of them are very similar, like there's a bar graph and a histogram. A lot of people think they're the same thing, but they're slightly different. So you need to pay attention closely. Okay? Don't just look at the pictures that I draw and say, oh yeah, that's that. Okay? Because they're slightly different. Also, there's something called a line graph and a descriptive polygon. They look identical if you just glance at them, but they're a little bit different, so you need to pay close attention. Okay? All right, so now the first thing we're going to do is called a stem and a leaf plot. I'm going to write down a list of numbers that represent the scores on an exam in a pre-calculus class. Okay, there we go. And now what we're going to do is we're going to do a stem and leaf plot. These are also known as Stemplots for short. Okay? And here's what you do. You divide each piece of data. How many pieces of data do we have right there? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. There's 31 pieces of data there. Okay, those are scores on a test. And what you do is you divide each piece of data into two pieces. The last significant digit, farthest to the left, becomes what's called the leaf, and all of the digits before that become the stem. Let me show you what I mean. So that 33 right there, okay? We divide that, we cut off the last digit, and that's called the leaf, and this is the stem. Okay? It's like the leaf is growing out of the stem. Okay, let's do the next one, the 42. It goes like that. Okay? Now, what's the purpose of doing that? It's not obvious yet, but I'll show you the purpose. Now, when we go to the next one, which is a 49, you see that has the same stem as the last one. So, I have 49. There's 49. Okay? And then what's next? There's another 49. So that's 49. You see, I have 3 leaves, 2, 9, and 9, all growing out of the same stem, 40. And that's right, whoops, and that's right here. 2, 9, and 9 are 3 different leaves with the same stem of 40. Okay? And then you continue in that pattern. So what's next? 53. So there's a new stem now. So 53. And then 55. And then 55. Now they need to be in order. Okay? The stems need to be in order from smallest to largest as you go down. I mean, I suppose you could do it from bottom to top if you wanted, but let's just keep it like we are. Here's what's crucially important. The leaves need to be in order, smallest to largest, as you go left to right. The smallest leaves need to be closest to the stem. Okay? That's easy to do here because these numbers are already in order, and so it's very easy to make the stem plot in the correct order. But if that data was not in the correct order, you would have to be very careful and make sure that when you do your stem plot, make sure you're doing it in order, smallest to largest. Okay, and here's another thing. Make sure the stems line up in columns. Very important. If you need to use graph paper in order to make that happen, then, well, if that's what you need to do, then do it. They have to line up vertically. The leaves do. Okay? Not by number. Look at that green column there. There's a 2 in between 2 3s. Okay? I'm not saying all the 2's line up and all the 3's line up. I'm saying that's the first leaf in each row. They need to line up vertically. The second leaves need to all line up vertically, and so on. You don't do that, it's wrong. Okay? All right, where do we leave off? We left off with the 55. How about if I cross them out as we go so we can keep track? So next we have 61. And then 63. And then 67. And then 68. Another 68. 2 69s. Now we're on a new stem. We have 72. 73. 74. And 78. And now our 80s. There's an 80, 83, and 3 88s. Okay, and next is 90, 92, 4 94s, a 96, and a 100. Now, this last one has 3 digits, right? So how do I break it? Where's the dividing between the stem and the leaf? Remember what I said. The last significant digit on the right is the leaf. So for this guy right here, here's the last significant digit on the right. So that's the leaf. Everything to the left of that is the stem. So I should put 10 there, which is actually not a 10, it's actually a 100. Okay, 100 and what? Well, just 100, so the leaf is a 0. Okay, so that's called a stem and leaf plot, or a stem plot. What's the purpose of that? Well, there's a few different purposes. One, which is a simple purpose, but it's still useful, is the fact that it saves a lot of writing. If you have several data points with the same stem, you don't have to keep recopying the stem part of it. Like, look at the 60s. There was 7 data points in the 60s. But I only wrote the 6 for those 60s one time. So it saved me from writing 6 sixes. You see what I'm saying? It's not a big deal, but it's a little deal, but it's still helpful. Okay, but more importantly, it helps you get an idea for how the stuff is laid out and clumped up. Look up here. Look up here. Even though those numbers are in order, when you glance at that list, you still don't get a very good idea of the layout of the different scores. But when you look down here, you can get a much better layout. What do you see? You see that the vast majority of the class got a D or better, right? I mean, assuming a 10-point grading scale. The vast majority of the class made it above that 60 mark, right? And in fact, a pretty large group of people got A's, didn't they? I mean, I can tell that by looking at the list of numbers above, but I can see it a lot faster by looking at the plot. Look how long the row is for the 90s, and then also the 100 on top of that. Those are all A's. I can very quickly see that there's 1, 2, 3, 4, 5, 6, 7, 8 A's. There's 7 in the 90s, and then there's 100. Okay? So it helps to organize the data, and it helps me begin the process of figuring out how the data is laid out, how it's clumped together, or if it is it even clumped together, or is it very spread out? You see what I'm saying? Okay. Now the rules for making a stem plot are the same, no matter how big or small the numbers are, no matter how many decimal places there are, even if there's decimal points, the rules are always the same. Look at this list of numbers here. Okay. The first data point is 1.1, right? So what's the leaf? The leaf is the 1. That's the rightmost significant digit. The rest is the stem. Okay, so notice that you can't tell by looking at what I just wrote that there's a decimal point there. Is that 1.1 or is that an 11? Okay, well, that's something that you have to look at your list of numbers, okay? You still need to have the list of numbers in order to see that there's decimal points there. So that you know that that's a 1.1 and not an 11, okay? Because the stem plot doesn't allow a place for the decimal point. You could say that that vertical line that I drew down the middle is like the decimal point. But what I'm saying is you wouldn't know that except if you looked at the list of numbers and saw, oh, there's a decimal point there. Okay. All right, what would be next? There's a 1.5, so how would I do that? I would just put a 5 there, right? And then there's a 2.3, and then a 2.5, and then a 2.7. And then a 3.2, a 3.3, and another 3.3, and then a 3.5, and a 3.8. and then there's a 4.0, 4.2, a 4.5, another 4.5, 4.7, and a 4.8. And then we have a 5.5 and a 5.6 and a 6.5 and a 6.7. And then notice there's nothing until 12.3. Okay, so what you need to do is you still need to include the stems for 7 point something, 8 point something, 9 point something, and so on, okay? But because there aren't any 7 point anythings in the list of data, then that means there's no leaves on that stem, okay? Same thing for 8 point something, 9 point something, 10 point something, 11 point something, and then we have a 12.3. Okay? This is what's called an outlier. It doesn't seem to belong with the rest of the data, which is neither good nor bad, right or wrong. It's just that those types of data points are called outliers. Okay? It might be bad or wrong. It might be that somebody recorded a number incorrectly. Maybe that was actually supposed to be a 1.23. That would seem to make a lot more sense. But we don't know that the data was recorded wrong or not, so we go with the data we've been given, and you just make a note to yourself, oh look, there's a number that doesn't seem to belong with the rest of the pattern. What's the pattern? The pattern is that the numbers are clumped between 1 and 7. Okay, actually very nicely clumped. They're in a nice tight little group with more in the center and less as you go out. And then you got that one outlier that's way out there. Now all of these, well, I say all, but these two examples, they both have the same number of, they go to the same decimal place. Like what I mean is this one up here, you see those are all whole numbers. And even though they have different numbers of digits, most of them have 2 digits, but the last one has 3. That just means that the stem is longer. And here, they all go to the tens decimal place. Okay, what would you do if there were some that went to the hundreds decimal place, but not all of them? Let me show you that. Okay, so look at this list. It's nice and short. So the thing about this list is not all of the data points have the same number of significant digits. This one's got 3 significant digits. This one only has 2, and this one has 4. Okay? That makes it a little tricky for the stem and leaf plot. And normally it wouldn't even happen, because when you collect data, you should really be deciding beforehand how many significant digits you're going to measure. Okay? How many significant digits you're going to record. You shouldn't really have a list of data where the different data points have different significant figures. If this one has 3, or I guess that's actually 4 significant figures, then, you know, if it goes out, I mean, what's the level of precision there? It goes out to the thousandths place, right? So then I would expect that you would be recording all of the data out to the thousandths place. And that 2.45, I would expect it to be written down as 2.450. And the 2.7 should really be 2.700. I mean, if you recorded this data point to the thousandths place, then why wouldn't you be recording them all to the thousandths place? your data list would actually look like that. Okay. Now we're not going to write out the stem plot for this because it would be huge, and I'm not sure if you can tell why, but here's the reason why. Because this first one here, what's the stem and what's the leaf? The leaf is just a 0. The leaf is always the last significant digit. So you see that would be 2, 4, 5. That's the stem, and then here's the leaf. Okay? And then, okay, I know you're already thinking this. What about the decimal point? You could put a decimal point there. That's fine. I mean, normally I would say you got to look at how you recorded the data to know where the decimal point is. But I'm fine if you put a decimal point right there. But my point is this. What's the next one? The next one is 2.700, right? So what would the stem be? The stem would be 2.70, and then the leaf would be the second 0. What's that going to mean for the size of my plot? It's going to be a long ways before I get to the next one, right? Because I would have to have 2.46, 2.47, 2.48, and I would go a long ways. And you can't do that, by the way, just put those dots. I'm just trying to make a point right now. I'd go a long ways before I ever got down to 2.700. Okay? But sometimes that's just what you have to do. Or if you think that that makes the whole thing pointless, then you might decide to round off to fewer decimal places. I'm not saying you should or should not do that. I'm saying that's one thing you could do. You might decide to only record to the tens place instead, and then you'd have this would be rounded off to 2.5, and then you have 2.7, and then 3.0, and 3.5, and 3.6, and then your stem plot would be much more manageable. There would be 2.5, there's 2.7, 3.0, 3.5, 3.6. If you feel that that is condensed too much, and now you've ruined your plot the other way, now instead of being too spread out, now it's too clumped up, then you could go in between, and you could say, well, let's go to the 100s decimal place. And this one would be 2.45, and then 2.70, 3.01, 3.50, 3.62. So you would have a 2.45, but then you would need to fill in 2.5, 2.6 with no leaves, and then a 2.70, nothing for 2.8, nothing for 2.9, and then a 3.01, nothing for 3.1 or 3.2 or 3.3 or 3.4, and then we would have a 3.50 and then a 3.62. So that's another way of doing it. Okay? So those are stem plots. Now, these are very nice in particular for if you want to combine two different sets of data in the same picture. As long as the data is in the same basic range. So let me show you what I mean by that. Okay, look here, I have two tables, and they show the age that the United States presidents were when they were inaugurated and the age they were when they died. And I've only included the presidents who have died. So I've left off Carter, the two Bushes, Clinton, Obama, and Trump, even though the book includes a lot of those. Okay, but I only included the ones that have died. So let's do a stem plot for the first table. Now they're not in numerical order, they're in the order in which they were inaugurated, so I need to be careful when I do this. I can't put necessarily this 57 here first, even if you might say this. What if I did this? 57, right? And then you might say, well, that's okay. If there's some 40s, it'll be easy to add that up above. That's true, it would be. The problem is not that. The problem is what if there's now a 56? My 7 is going to be in the way. Okay, so here's what I'm going to do. I'm going to look carefully and I'm going to look at all the 50s. Okay, let's do this. Just bear with me. Watch this. I'm going to find all the 50s because the first one is a 57. Okay, or let's not do that. Let me start over here. Let's do this. Let's look at the table and let's see if we can find the smallest decade at least. We don't have to find the smallest number, but I see there's some 50s and 60s, all 50s and 60s, but then I see there's some 40s, okay. And I scan through the table, I don't see any 30s, so the smallest decade is 40s. So let's find all of them in there 40s. So that's going to be our first stem. It's going to be a 4 for 40. So let's find all of those. And you want to be careful. You don't want to miss any, or else you're going to have to come back and erase things. You can't just add them back in always. So sometimes you get lucky, but not always. So I'm going to double check. Okay, I think I got all the 40s. So for that one now, it's pretty easy to find. The smallest one is 42. And then there's a 43. And then a 46, a 47, and a 48. And two 49s. Okay, now let's do the 50s. I'll go ahead and put my stem there. Okay, let's find the 50s. There's a lot of them. What's that mean? It means that this stem's going to have a lot of leaves. Okay. Now since there's so many, I need to be careful. And here's what I'm going to ask myself. I'm not going to just say, let's find the smallest one. Since there's so many, I'm going to start at the number 50 and see if there's any 50s. Ah, there is one. Okay. All right, any more 50s? No, but I see a bunch of 51s. How many 51s? 1, 2, 3, 4, 5 51s. Okay, I see a 52. I don't see any 53s, but I see 4 54s. Well, I've gone off the side of the screen, haven't I? Let me shrink this down here. There we go. And a bunch of 55s, I think. Let's see. 1, 2, 3, 4. Well, there's only 4 of them. Okay, so there's 4 55s. I'm going to have to shrink it more to fit. So I said 4 55s. And then 3 56s. Four 57s. And a 58. Okay, so there we go with all the 50s. All right. Let's find our 60s. Okay, double checking, make sure I don't miss any. Okay, so I see a 60 and 2 61s. And a 62. A 64 and a 65. And a 68 and a 69. Okay, there we go. So that's all of them. Okay. Now, let's do a stem plot for the ages at death. Now, here's the thing. The stems aren't going to be exactly the same, but they're not that far off. They're in the same basic range. So watch what I can do. Let me move this down here so I can make it bigger again. Okay. So this is going to be age at inauguration. Okay, now watch what I'm going to do for age at death. I'm going to use the same stems and grow the other direction. So let's see. Where's the 40s? It's not going to be that many. Not very many presidents died in their 40s. By the way, in the first chart, Cleveland was listed twice because he was president twice. But in the second chart, he's only listed once because he only died once. Same with all the other presidents that had more than one term. Okay, so I lost my place. Where am I? I'm looking for 40s. Okay. So there's a 46 and a 49, right? I'm going to use the same 40 stem. I'm going to grow the other direction. Now in this case, because I'm going the other way, see, you want the smallest leaf to be closest to the stem. So I'm going to put the 46 like that, and then the 49 like that. Okay? Now let's find the 50s. These will be more spread out. Okay, 53, 56, 57, and 58. 3, 6, 7, and 8. Now let's do our 60s. Got Got to be really careful. You don't want to miss anything, because if you have to go back and add something in, you're probably going to have to erase a lot of stuff and redo it. So take your time. Oh, whoops. See, I made a mistake. I'm doing 60s now, and then I switched to 50s. I already did the 50s. Okay, I hope that's all of them there. So let's see. There's a bunch, so I'm just going to start and ask myself, is there any 60s? And I don't see any. Oh, yes, I do. There's 160. Is there any 61s? Oh, there's another 60. See, I'm starting to go faster, and I'm also starting to make mistakes. So luckily, I'm catching them before I write down anything. But I better be more careful. Okay, I don't see any 62s, but I see two 63s. And two 64s. One 65 and 166. Now I see many 67s. I see three 67s and a 68. And you want to ignore the impulse, if you think you're running out of room, to start writing the numbers smaller. Try instead to give yourself more room. Okay, now 70s. Okay, I hope I got them all. Now there's no stem for 70s yet, so I need to start by writing that. And there's a 70 and two 71s and a 73 and a 74. Remember, you have to keep your leaves lined up vertically with the leaves above them and below them. Okay, where are we now? There's a 77, two 78s, and there's a 79. Okay, 80s. I see an 80 and an 81 and an 83 and an 85 and an 88. And then this will be our last row, will be the 90s. Not very many of them. There's two 90s and two 93s. Okay, so there we go. And that's age at death. So you see that I'm able to combine two different tables in basically one stem plot. It's really two stem plots, but I'm able to reuse the stems. So it's easy to compare, not just to describe each table. Like I can instantly see by looking at the stem plot that the ages at inauguration, I can see something very important that you technically could see in the table, but not very easily. And that is that every president we've had who has died, I have left out the ones that are still living, every single one of them was in their 40s, 50s, or 60s. That's a pretty small range. and the vast majority of them were in their 50s. I did not know that before, that most of the presidents were in their 50s when they were inaugurated. And I can also see from the other side of the stem plot a lot of stuff about the second table. I can see that their ages at death are spread out from 40s to 90s, mostly in the 60s and 70s. And not only can I see those descriptions of each table, but I can see a comparison between the two tables as well. You can see that, and of course this is not surprising, because we live longer, but you can see that the ages at which the presidents have died, compare that to the ages at which they are inaugurated. And you can see there's a much shorter range, a much smaller range of the ages at inauguration. There's just from 42 to 69, so just a 30-year gap basically. All of the presidents have been in those 30-year age gap when they're inaugurated, but at the same time in the same plot I can see that when they died they're much more spread out, from 46 to 93. So that's almost a 50-year age gap. Okay. All right, I think that's about it for stem plots.